Alright, chapter 9, the last chapter. Discrete math, let's go. No further intro, no further messing around, no wasting time. And nobody got time for that. People want to get to the work, people. So none of that wasted time. None of that talking about nonsense. Busy, gotta go. Okay, so a store sells 5 shirts, 3 pairs of pants, and 4 shoes. How many distinct outfits can be made? This is what we would call an independent choices question because basically we can find the answer by multiplying the number of possibilities for each choice. We have 5 choices for shirts, 3 pairs choices for pants, 4 choices for shoes. And we're not mixing up the shoes. Come on, guys. You gotta wear a matching pair of shoes. And if you do that, you would get 15 times 4, you get 60. Okay, that's the fundamental theorem. No, fundamental counting principle. How many distinct ways can the letters of cappuccino be arranged? Okay, so this is a similar concept. 1, 2, 3, 4. We've got 3 C's, 1 A, 2 P's, 1 U, 1 I, 1 N, 1 O. Wait, what? 0 O's. Okay, so we've got 4, 6, 8, 10 letters in cappuccino. So it should be, right, 10 times 9 times 8, da-da-da-da. Wrong, because we have some repeated letters. So what we do, we count the total number of letters. Let's just verify that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10 factorial ways to rearrange them, but there will be some rearrangements that are not distinct. They're the same because of the repeated letters like C. So what you do is you divide by the number of ways to rearrange the C's, which is 3 factorial, the number of ways to rearrange the P's. Now technically, we can also do divided by 1 factorial, 1 factorial, 1 factorial, 1 factorial. Those would just go to 1 though, so this is what we need. Okay, so let me continue writing this. You get this. Because the 3 factorial would cut off the 3 and the 2, times 2 times 1. Let's do this. Use this to cancel out. Let's just use this to cancel out this. Let's not complain about the calculation. Let's just do it. What do we got here? We've got 10 times 72 times 42 times 10. Okay, and this over 1. So what do we've got here? We've got 100 times 72 times 42. What's 72 times 42? It is 14, 8, 28. So it is 4, 2, 1, 0, 1, 3, 0, 2, 4. 100 times 3024. There it is. I don't like cappuccino, I like latte. Cappuccino too foamy. How many students can students be chosen from a group of 10? And that's just 10 choose 3. Notice they're not talking about any kind of rearrangement or order. So it's just the number of things you can choose from divided by the number of 3. Which turns out to be, okay, if you had 10 students and you wanted to rearrange 3 of them, you would do this. 10 times 9 times 8. But then there's 3 factorial ways to rearrange them, hence the formula. You should just memorize this formula, right? 10 choose 3 is that's the formula. So it does become 10 times 9 times 8 over 3 times 2. Do some canceling. That goes to 3. That goes to 4. 30 times 4, 120. 10 choose 3 is 120. Okay, using this, we can do binomial expansion. Okay. This term in this expansion, let's think about this expansion. let's just write the first term. The first term would be 100, choose 0, which is 1, times the first term of the binomial to the 100th power, times the second to the 0 power. Well, that's not what we want. So let's write the second term. It could be 100, choose 1. This is the way I do binomial expansions, 3 parts. 1 from combinations, also you could say it's from Pascal's triangle. Then the first term to some power, second term to some power. And it's 0, 1, 2, and on to 100. The power here diminishes, goes down. The power here goes up. And the powers have to add to 100. So that's obviously not also what but what I've now seen is this term is going to be 100, 99, 98, 97. So that term is going to be 100, choose 3. 2, 3. It's going to be 3a to the 97th. And 2 down. And then just by adding up, this has to be 3. Well, because it says it's 3. Okay, so how do we get the answer here? It's probably not going to be these guys. But what we can do is 3, we can use exponent rules. Raise each factor to 97th power. Raise each factor to the 3rd power. And I'm still not sure of the answer. But what I can say, one more step here is to say, okay, put the variables together, put the numbers together, and say that 9 is 3 squared. So we can change 9 to the 3rd as 3 squared to the 3rd. And then we have the exponents, which aren't important. And so what do we have here? We've got 100, choose 3. We've got 3 to the 97. And we've got 3 to the 6th. When you have a power to a power, 3 to the 6th. And then what can you do when you've got the same base to powers? You can add the powers. 97 plus 6. Bombino. Okay. The Dondada. X squared term. Similar concept here. Each term can be broken down into 4, choose something because the power is 4. Like here it was 100, choose something because the power is 100. First term is 2x to some power. Second term is 3 to some power. So I'm pausing to say, okay, if this is the only term with the x, we know this has to be the second. Because it's an overall power of 4, we know this also needs to be the second because they have to add up to 4. And we know the x squared term is going to be the 3rd term. In other words, it's like the first term is going to be based on 4, choose 0. Second term, 4, choose 1. Third term, 4, choose 2. And we know this is going to be the 3rd term because the first one's going to be x to the 4th, then x cubed, then x squared. So this should be giving us our answer here. So 4 choose 2 is 4 factorial over 2 factorial, 2 factorial. Now, be careful here because we now have 2 squared times x squared times 3 squared. So what we have here is a little simplifying. We have 4 factorial over 2 factorial cancels to this, times 2. We got times 4, we got times 9. And we don't need the x squared, we just need the coefficient. So let's do some canceling. That cancels with that. So we've got 12 times 18. We've got 180 plus 36. Yeah, 180 plus 36. Because it's 10 times 18 is 180, 2 times 18 is 36. All right, not bad. All right, everybody, we're back where it all began, the canteen. Let's finish this off. The first 5 terms of the geometric sequence are such and such. What is the explicit formula for the nth term? Okay, so usually geometric sequence, we're going to use this formula. First term times common ratio to the n minus 1. That's the normal form we would go for. And we know a few things already. We know the first term is 3. And we can figure out the common ratio. Remember how we can do the common ratio. Do one term divided by the previous term before it. For instance, 12 divided by 6 is 2. And we could also do the second divided by the first and get the same result, 2. Common ratio is 2. So we've got here 3 times 2 to the n minus 1. Okay. So that would leave us with a. You can always plug in and check, right? Plug in to check if you got the same result. Just to be careful. Okay, which of the following is true about the sequence? Okay, so remember, theoretically, we could write out a bunch of terms of the sequence, right? What's b sub 1? It's 6 over negative 1, it's negative 6. What's b sub 2? It's 5 times 4, 21 over 5. What? Sure. We could do that. Is that right? I think it is. We could write a bunch of terms out and we could see what it converges to. And that's something you could do if you have extra time, if you want to verify, or at least get some concept of verification of what's going to. Right, that's like 3 or something, approximately. But if it's a complex formula like this, probably not. Well, if you have time, you can do it, but the better way to do it, this is a rational situation here. It's a rational function. We know we can use the same logic as we use for rational functions with the domain of all real numbers. Or sorry, the domain of real numbers. Compare the degree. We've got degree 2 in the top, degree 2 in the bottom. Same degree means we're gonna just divide the first terms. Basically, all rational functions are like division, and we can just divide the first terms and we get 5 over 2. This should converge to 2.5. And this does kind of seem like it is going to converge. I'll just do one more term just in case, just for reference. So we get 16 is 5 times 16 is 81 over 32 minus 3 is 29. So that's like 2 point something or other. It's going closer to 2.5. But the main point, if it's a rational equation, polynomial over polynomial, compare the degrees. Same thing here, rational, compare the degrees. Degree 1 over degree 1. So we can just focus in on the first terms and say 4n over 2n is 2. Is going to converge to 2. As you plug bigger and bigger n values in, this constants don't matter. It just becomes 4n over 2n, which is 2. Same thing over here. Constants don't matter. It's just 5n squared over 2n squared, which is 2.5. What is the value of the expression below? Okay, this is just testing our knowledge of summation / sigma notation. So this means we're going to have 3 times something minus 2 added up repeatedly. Add it up. And so this tells us what form each of our terms is. And this tells us what our first input is, 1. Then we just keep going. 1, 2, the next one's going to be 3. And we stop when we reach this. So we need one more. We need one more, and then we just simplify. So it's 3 minus 2 is 1, 6 minus 2 is 4, 9 minus 2 is 7. Oh, it's an arithmetic series. Arithmetic series. So we could add that up, or we could use the arithmetic series formula and say it's first term plus last term divided by 2 times the number of terms is 4. It's 22. Or we could just do 5 plus 17 is 22. Okay, oh, it's the same thing, but so this is basically, we could put this into sigma notation if we wanted to. because it's an arithmetic sequence, but we can just use this formula. Formula for arithmetic series, a sub 1 plus a sub n, first term plus last term, divided by 2 times by the number of terms. So we know a sub 1 is 5. We know a sub n is 41. So we just need to find what n is. How many terms are there? We could list them all out if we have time. Or we could remember that these are terms in a sequence, which has to follow the arithmetic sequence rule, which is first term plus common difference times n minus 1 is a sub n. So if we want to find which term 41 is, just plug in here. We know the common difference is 4, right? 13 minus 9 is 4, 9 minus 5 is 4. And we can solve to find what n is. Subtract 5 from both sides. Divide both sides by 4. N is 10. Plug that in. Calculate. So we got 46 over 2 times 10. 23 times 10. 230. Oh, who are these noisy boysies? Okay. There it is. All right. Last 2 pages. What is the sum of the first 5 terms of the geometric sequence? Okay, so sum, again, we know it's a series. What's the formula? Well, again, a test, they're not going to give you only 5 terms. You got to actually, because then you could just list out what they are, right? It's 4, it's 12, it's 36, it's 108, it's 324. But you can kind of get an idea. Oh, that's not helpful. Okay, let's use the formula. You got to memorize this formula. Mr. Redmond has it memorized. The formula is g sub 1, I'm going to write it here, g sub 1 minus g sub 1 times r to the n, all over, my eraser, where's my eraser? Who took my eraser? All over 1 minus r. Fine, I can't find my eraser. So it's first term, 4, minus 4 times the common ratio is 3. 5 terms, 1 minus the common ratio. So what do we got here? We've got, if I multiply everything by -1 over -1, it becomes 4 times 3 to the 5th minus 4 over 2. That could help us a little bit because then we can cancel out and we get 2 times 3 to the 5th minus 2. 3 to the 5th is 3 squared is 9. 3 cubed is 27. 3 to the 4th, 81. 3 to the 5th is 243. 2 times 243 minus 2. 486 minus 2. That's what I got. Okay. I'm pretending like I can find my eraser here, but I should just, for the sake of the audience, just give up. Okay. What's next? This guy. Okay, this is an infinite geometric series. So the formula here is g sub 1, the infinite geometric series, over 1 minus r, if and only if our common ratio has an absolute value less than 1, because then it will converge down. The terms will converge, and therefore the series, in this case, would converge. So what's the common ratio? That's the key. Well, let's do the trick, or not the trick, but the strategy of doing 1 term divided by the term before it. 4 divided by 8, oh, that's 1/2. 2 divided by 1 is 1/2 also. It's a common ratio of 1/2. So So if the common ratio is 1/2, this will converge. And the rule again is simply, if the absolute value of the common ratio is less than 1, it's going to converge. It doesn't matter what the first term is. All that matters is the common ratio is less than 1 when you take the absolute value. So, right, so negative 1/2 would also converge. The absolute value has to be less than 1. Like this. This would converge even if it's infinite, but that's not what it's asking. It's asking for the fourth partial sum. So remember what that means. That basically means we're adding up the first 4 terms. So you don't have to write out the sigma notation, but I will anyways. Well, actually, technically, we could just add these up, or I'm going to use the same formula because a partial sum is basically a finite series. So we're basically adding the first 4 terms of this. Okay, get to the point. We need the common ratio. Again, common ratio is found using this calculation. So R2 over R1 will be equal to R3 over R2, or any term divided by the previous term. So what's 72 over 96? Let's simplify that a bit by like dividing by 4 or something. So that becomes 18 over 24, and I recognize that as 3/4. That's the common ratio, 3/4. You could also check here, this times 3, this times 4 is 3/4. Okay, so finally, we can use this formula up here. First term minus first term times common ratio to the number of terms we're adding, fourth partial sum, 1 minus common ratio. So what we have here is, this is where I need my eraser. It should be 96. What we have here is 96 minus 96 times 3 to the 4th over 4 to the 4th. I think this will help us simplify if I write like that, over 1/4. Now, dividing by 1/4 is the same thing as multiplying by 4. We get this. Now, if I distribute this out, this is going to be big. So we get here 4 times 96 is, well, 4 times 100 is 400. It's 16 less than that. It's 384. And then we've got, distribute this here, 96. Where's my eraser? Gar! I'm gonna break this into 4 times 28. You'll see why in a moment. Okay, if we break 96 down into 4 times 24, okay, then what do we have here? We've got 384 minus, we can do some canceling in a moment, but we're gonna get 4 times 6, which is 24 is equivalent to. Now this 4 and this 4 to the 4th cancel out and give us 3 to the 4th over 4 cubed. Okay, keep bringing down the 384. Now here we go. We've got 2 4s and 1 4. So I'm going to keep the 6, but these 2 4s cancel out. And then we're just left with 1 4 in the denominator. 3 to the 4th over 4. Okay, I'm going to keep going here. 384, 6 over 4 becomes, we divide by 2, we got 3, divide by 2, we've got 2. So it's 3 to the 5th over 2. And we know 3 to the 5th, based on that, is 243. So it's 384. Minus 243 over 2, which is 384 minus 121.5. So it's 262.5. Yes. Finally. 262.5. That's our answer. Easier because what do we have here? We've got an infinite series. You don't have to write this out, but I will. We've got first term times common ratio is 1/5. Easiest way to see that is 1/5 divided by 1 is 1/5. 1 divided by 5 is 1/5. 5 divided by 25 is 1/5. What does that equal to? This simple formula. Here, the common ratio is less than 1. It's 1/5. So we can just plug directly into this formula. First term over 1 minus common ratio is 25 over 4/5 is 5 over 4 times 25 is 125 over 4. This is like 31.25, which makes sense. All right. George has 2 different books. 5 different books, sorry. He's choosing which books to tank on vacation. How many possible groups of books can he tank if he must tank at least one book but could tank any other amount, including all 5? Okay. This is a combinatorics problem from chapter 9, section 1. And remember, we had many different types of problems. Here's the key to tell you which problem it is. He could tank at least one book, but he could tank any other amount. When you do not have a set amount, you can't use combinations, you can't use permutations. You have to do something different. And in our case, that's always going to be a subset selection problem. And so remember, we had a lot of these with like pizza toppings. And the logic is, okay, treat this as a set of 5 choices, binary choices. We've got book 1, we've got book 2, we've got book 3, on down the line to book 5. And we're saying, you're just saying yes or no to each of these books. So if you say yes or no to each of these books, you have 2 choices for each of these books. You have 2 to the 5th possibilities, right? You could say yes to the first 4 and then no to that. That would be the first 4 books. Or you could say yes to only the first book and no to everything else. That would be only the first book. So it's basically 2 choices multiplied by 5 times 2 to the 5th. But 2 to the 5th is 2 to the 5th is 32. Why is that not an answer? Because you must tank at least one book. In other words, the one thing you can't do is no, 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 no. He's trying to get no book so he can just be on his device the whole vacation. No, reading is fundamental. You need to read. Don't use your device. You can't say no to all the books. So you subtract 1, 31. So again, subset selection because the size of the group is not fixed. You could have 1, 2, 3, 4, 5. Okay, just testing our knowledge of recursive formula. So remember how this works. First term is 1. Second term is saying it is 2 times the previous term. N minus 1 implies the previous term. So the second term is 2 times the first term, which is 1, 2. Not that. Third term is N is 3 times a sub 2. So it is 3 times previous term of 2, 6. Ooh, I know what this is. Fourth term is N equals 4, so it's 4 times a sub 3. A sub 3 was 6. Oh, this is a very clever way to talk about the factorials. This is 1 factorial, 2 factorial, 3 factorial, 4 factorial. But I know the answer is C. So, right, that sequence is neither arithmetic nor geometric. Sequences can be just any pattern. It doesn't have to be arithmetic or geometric. Well, here we go. Which rule would give an arithmetic sequence? So this would give geometric. You could write out the first few terms, 5, 10, 20, etc. Not arithmetic because 20 minus 10 is 10, 10 minus 5 is not 10. No common difference. Well, the answer is this, right? Because you would get 5, then you plug in 2, you would get 3, 1, -1. You get a common difference of -2. Whereas this, you would get 11, 14, 19. 19 minus 14 is 5, 14 minus 11 is 3, no common difference. Similar concept here, no common difference. Well, let's just verify. So you get 10 plus 2 is 12, 20 plus 1 is 21, 30 plus 2/3, heck nah. Common difference, the difference here is not an integer, certainly not 9. So no common difference, not arithmetic. All right, you could also recognize the arithmetic sequence formula. First term plus common difference times n minus 1. All right, we're almost there. Right, so this guy brings up the point. I had to get at least 3 terms for each of these if I wanted to verify it was not arithmetic, because you can find the difference. Any sequence, you can find the difference between 2 terms. You need to see if there's a common difference, which means you need to check 2 differences and see if they're the same. So here, for instance, this looks like a geometric sequence because it's multiplied by 3. But we can't prove it's geometric if we can't compare 2 ratios to see if they're a common ratio. So, we're told it's arithmetic. We're trying to find a term. So, okay, we need the 8th term of something that has, we don't know, plus a common difference times n minus 1. Let's see what we can figure out. Technically, we don't know the first term other than k, but we could try to plug in k. D, what's the common difference? Well, let's find the first difference. A sub 2 minus a sub 1 is 3k minus k. If this is in fact arithmetic, then this difference has to be the same between each pair of terms. So that must be the common difference. And we're trying to find the 8th term. So 8 minus 1 is 7. So the 8th term is k plus 14k. Kind of did this problem out of order, didn't I? It's 15k. But I didn't find what k is yet, so that was kind of backwards there. I need to use this. The 5th term is 144. So let's plug in for the 5th term here. The 5th term is 144, and the 5th term must be k plus 2k times 5 minus 1. So that's telling us that 144 equals k plus 8k, 9k. Now we can solve for k. 144 divided by 9. Modeling good testing the habits of showing your work. Do the division on the side, why not? 16. So there we go. Our answer is 15 times k, 15 times 16 then. And that, again, I could show the work on the side, why not? 0, 3, 5, 8, 0, 6, 1, 240. And here we go, almost there. The sequence is arithmetic. So this is modeling the short answer type questions that you will see on the second part of the comp. So it just is, the problem's not that difficult, but this is this is what they look like. So let's just talk about good test taking habits. Again, take your time, be sure. What is the 10th term of the sequence? I write down this formula because I know I'm going to use it. I write down the information carefully. First term is negative 17. Common difference. Let's be careful and say, okay, we could do 9 minus negative 4 is 13. Or we could do negative 4 minus negative 17 is also 13. So the common difference is 13. And then we want the 10th term. So the 10th term is negative 17 plus 13 times 10 minus 1, which is negative 17 plus 13 times 9, which is negative 17 plus 117. 100. And how many terms are in the sequence? We can use the same formula again. A sub n is negative 17 plus 13 times n minus 1. And we want to know how many terms are in the sequence. So we want to know which term this is. What n gives you that? You could distribute this out, but actually it's not going to save you any steps because add 17 to both sides, you get 195. You can just divide straight from here. And n minus 1 will be whatever this is. How many times does 13 go into 195? It goes in 15 times. Therefore, n is 16. 16 terms. Make sure you box your answers. We're going to take a short answer, and we have done it. We've reached the end. Keep working hard, guys. Keep asking questions. Keep going to that finish line. You're almost there. You guys are going to do great. Just remember, go blue.